This video is going to cover Earth systems. What is a system? What are the different types of systems? And how inputs and conversions to outputs can affect a system by providing different feedback signals. So, those are things that we will be covering in this video. Starting with what is a system? Listed here in the bullet points is the definition from a textbook, our textbook. Um, it is any ordered and interrelated set of things. Um, the inputs that go into the system, whether they are energy or matter, how they are linked together, how they change, and includes the outputs as well. What is the effect of all of those inputs and changes, how they're related to each other, and how they might affect each other and the system itself. So the all of those elements of the system uh, can be related to each other, interwoven. They might occur in a series, like there's thing A, then thing B, then thing C happens, thing D, in a directional sort of way, or we might have um, input A interacting with D, but D interacting with B, and then maybe B interacting with A, and so there can be a lot of back and forth, sort of like a web being woven, in that sense. And a system can be made up of any number of subsystems, meaning that we could be looking at a very large, complex system. And within that large, complex system, we can identify smaller systems. And so, an example of that is Earth as a system. Earth, of course, we have many various processes happening. And so we can break down Earth as a system into countless subsystems, um, which we'll kind of address a little bit later. But I did want to address on this slide two types of systems: an open system and a closed system. What is the difference between those? Now, most systems in nature, they are open systems. This means that energy and matter as inputs, they will flow into the system, and some conversions might occur, and then we have outputs as energy and matter outputs. So Earth is an open system, at least in terms of energy. And we could debate this a little bit. Because as an open system, the Earth certainly receives solar energy, and it will reflect heat energy back out uh, into space. It will, uh, well, that's the main idea here in terms of energy. As an open system, it receives the energy and reflects it back out to space. Um, a closed system, on the other hand, is entirely self-contained. And this rarely happens in nature because it involves um, this system to be making its own energy and consuming its own matter and then making new matter. And so that just doesn't really happen naturally. There's some engineers that work and physicists that work to try to create closed systems, but rare in nature. Now, where I said Earth is an open system in terms of energy, it can be considered a closed system in terms of matter. And that's because we generally don't think of big chunks of Earth flying off off the planet and into space. Um, that's certainly not happening today. However, if any of you can think of some examples of matter as an input, where might we be accumulating matter from space? And it comes to Earth, incorporates into Earth, technically. Um, Meteorites can be an example. They're small. They're small compared to the rest of Earth, or at least we want them to be small. We don't want any large meteorites impacting Earth. Same with comets or asteroids. But still, technically speaking, that is matter coming into Earth. And if we think about all the satellites we've launched into space, again, technically, those satellites are made with Earth materials, and we have launched them out into space. So, in terms of matter, we could quibble about specifics. But I will say, um, for exam purposes, that we will consider Earth um, an open system in terms of energy and matter. Let's say that. Um, so those are two different ways of looking at systems. But again, because we're dealing with natural processes, well, even human generated processes, most of the time they are open systems. And so an example of that is a car. Now, this is a human-made system, but I think it's a great illustration of how an open system works with inputs, with energy and matter. There's actions and conversions of that energy and material. And then we have outputs, which, is the car being able to run and heat being given off from the uh, combustion engine or even the electric cars. They give off heat um, with their batteries. But other inputs um, here, inputs, we have to put gasoline in the car, or you have to charge the electric car. Um, the combustion engines need oxygen. We need oil to lubricate all the moving parts. We got to have good functioning tires, so we have traction on the road. Other resources just to literally repair the car and to make payments. You can't have a car if you don't make payments on it. So all of those are inputs we put into the car so we can keep the car so the car stays running. That's the conversion and storage actions. And then finally, the outputs from all of that. Again, with combustion engines, we have exhaust, we have heat. Um, with any car, it will move as long as we keep it up. Changing the oil every now and then, replacing the tires, other repairs that have to occur, and then with all the payments we make, we have debt. So all of those things um, make up this open system because we have to keep putting in these inputs and we keep getting the outputs. It's definitely not a self-sustaining system at all. So that's one example. A natural example of an open system is plants. Plants are open systems. Um, I have questions here. What make up the inputs for this plant? What is it taking in? What are some of the conversions that are happening? And then what are the outputs? So we have inputs. Anywhere you see the arrows going into the plant, those are our inputs. So plants need sunlight. They take in oxygen and carbon dioxide. They need to be watered. Fertilizer certainly helps the plant grow. And then here in the green box, that's all of our energy and matter conversions. So we have photosynthesis occurring, that gives the plant food, essentially. And then there's respiration that occurs as well, um, which converts those sugars, the plant's food, converts them into energy for the plant growth. And so the output here, essentially, the plant can live, and or that's part of the conversion process, I guess. The plant has life and grows, but the plant will also give off heat. It will give off oxygen and carbon dioxide, and then it does produce dead organic matter as the leaves grow and fall off. Other debris from different kinds of plants give off different kind of debris. But that's an example of a natural open system. We have the inputs. In this case, the plant grows, it thrives with the right kind of inputs, and then it gives off certain outputs as part of its life processes. So, as part of the systems topic, um, I want to talk a bit about system feedback because the feedback, uh, generally speaking, feedback is how a system responds to the inputs. So, we're going to talk about positive and negative feedback, but I don't want us thinking that positive and negative means good or bad. That's not what those terms refer to. Positive feedback means that the inputs are encouraging increased responses from the system. So the system will grow, or the responses from the system will grow. It doesn't have to be physical necessarily. But an example of positive feedback is what's called the snowball effect. And that's a phrase that people use to describe something that's kind of getting out of hand, getting away from them. This is totally snowballing uh, from me. And we could think of it like taking a snowball and rolling it down a hill. As it rolls down the snow covered hill, the snowball will get bigger and bigger and bigger. That is the positive feedback. You're kind of adding snow. The gravity is just kind of helping that snowball roll down the hill. So all of that information um, has the snowball getting bigger and bigger. The system there is growing. Snowball is growing. And it will continue to grow until it reaches the bottom of the hill. And so that, the snowball getting to the bottom of the hill, that would actually be a negative feedback. We got rid of the addition of snow. It ran out of hill, no more gravity causing it to move. And so this negative feedback is discouraging responses from the system. And so the snowball's no longer growing. We can think of negative feedback like self-regulation or stabilization. Again, the bottom of the hill, no more snowballing. The snowball just kind of sits there, not growing anymore. The one thing about the positive and negative feedbacks is that it can depend on how you define the system. And so we're going to look at some examples of that. Predator-prey feedback is a good example of a feedback loop, but I'm going to ask you, is it positive or negative feedback? So where do we start here? Doesn't really matter. I'm going to start in the top left with all these rabbits. So there's a large population of rabbits in some hypothetical place. Well, lots of rabbits means there's lots of food for the predators. And so that can attract predators. It creates a favorable environment for predators. And so the predator population gets larger and larger. Except as we have more cougars, well, more cougars mean they're going to eat more and more of the rabbits. So the rabbit population falls. Well, now it can't support all those many cougars. And so with decreasing food supply, well, the cougar population also decreases to kind of match with the prey population that can support it. But now with less predators, well, now the rabbits can reproduce and the prey population goes up again. And then with a larger food supply, well, now we can have more cougars and et cetera, around the loop we go. So, whoops. So is that loop positive or negative feedback? Are we growing the system as we go around the whole loop? At times it grows, right? At times there's more rabbits or more cougars. But there's also times when the prey and the predator population falls again. So is this a system running wildly out of control with a positive feedback loop? Or is it self-regulating itself with predator prey populations rising and falling and rising and falling? It is negative feedback. This is a negative feedback loop. One of the species population, it rises, but then so does the predator population and then cuts it back down. And then the predator population goes back down. So I hope that makes sense as just one example of a feedback loop. There's another example here where we are looking at um, temperatures, speaking more on like global temperatures and sea ice. So sea ice, we find a lot of sea ice around the North Pole. It's in the Arctic Ocean. And when the global temperatures rise, it also means the ocean temperatures are rising, but the sea ice is going to melt. Right? Ice will melt if the temperatures rise high enough. But what happens in the ocean is that the ice itself, the ice and the snow, uh, it's white, which is very light in color. But the water itself, it acts as more of a dark color. And so if we're looking at sunlight, sunlight is going to absorb into the darker ocean. And as sea ice melts, there's more of that darker ocean surface exposed. And so more sun is being, uh, more solar heat is being absorbed by the ocean. And so we have a decrease of reflectivity. It's also called albedo, it's the fancy word, um, meaning that just the ocean is absorbing more sunlight, more heat. And so as the ocean absorbs more heat, temperatures rise some more. Temperatures rising means more sea ice melts, exposing even more of the ocean surface. So albedo goes down even more. Ocean absorbs or even more heat, meaning temperatures are rising. And around we go here. Now, what kind of feedback is this? Positive or negative? Are we having a system kind of running away with itself? Or are we regulating things? In this case, temperature, I suppose, is what we'd be regulating, or the amount of sea ice that is present. Are we regulating that, or are we getting more and more of something without a check on it? In this case, it is a positive feedback loop. Temperatures just keep rising, sea ice keeps melting, ocean keeps absorbing more heat, leading to more temperature rising. And so, in that case, in that sense, it is a snowball effect. It is a positive feedback loop. One of the last things here in terms of Earth systems is the idea of equilibria within a system. And so with these feedbacks that we were talking about, that's pretty much related here to equilibrium. We have two types of equilibria that Earth systems operate under. We have some systems that experience just steady state equilibrium. And that means that while there might be small changes over time, over maybe shorter time periods, over longer time periods, we have a stable average. So, looking at this little makeshift graph on the bottom left, we have these small squiggles going up and down representing system operation, increasing the system operation, decreasing, increasing, decreasing. But over this long time period, there's not a lot of change. And so, an example here, I'm just gonna, this is a slightly problematic example, but just maybe over the course of a year. No, I don't like that example, sorry. Um, I'll think of an example later, maybe. But that's the steady state um, equilibria. Small changes on a short term, but uh, generally stable uh, over a longer period of time. Dynamic equilibrium, on the other hand, this is a system that also has short-term changes, as we can see by the squiggles, but it is also changing over the long term. Ups and downs, what have you, depends on what the system is, what's going on. Um, we can also, especially with dynamic equilibria, we can reach a point in that system operation where a threshold is reached, and that is a point where the system becomes very destabilized. It can no longer really uh, keep functioning in the way that it has been with the trend that these operations were taking. It finally gets to a point where it goes, nope, and there can be a very abrupt shift and change in that system until it reaches a new point where it can kind of restabilize itself. So that threshold is the point where the system is no longer stable. I sometimes think of this like a river. This isn't the best example, but during a flood, the river level is rising, 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 rising until it gets to a point where it might be overflowing its banks. That would be its new threshold, just kind of releasing all of that water because it can't hold it anymore. And then eventually the flood waters recede and it goes back to its regular flow level. But that's at least one example of a dynamic equilibria condition. And um, talking about Earth as a system and it being nope, made up of subsystems, Earth, as one big system, has four spheres or four main systems. We are going to focus on the first two on this list, the lithosphere and the hydrosphere. But we'll touch on atmosphere and biosphere as we go through the chapter or through class. The lithosphere is made up of all of the solid part of Earth, the crust, the mantle, the core, the rocks, the sediments. That's all part of the lithosphere. The hydrosphere is all of the water on the planet. So all the oceans, the lakes, the rivers, and the ice as well, snow, and the ice caps, glaciers, all of that is included in the hydrosphere, which is why we have a whole chapter um, looking at glaciers. Then there's the atmosphere, which all the gases that surround the Earth, oxygen, carbon dioxide, methane, nitrogen, uh, it also, we would talk about the weather if we were dealing with the atmosphere. Um, and then the biosphere, finally, that includes all the living things on the planet. So people, plants, and animals, but also includes bacteria, um, the little tiny microbes that live in the soils. That's part of the biosphere too. So like I said, we are going to focus on the lithosphere, the hydrosphere, their interaction with each other. But do know that all four of these spheres interact with each other in many complex and diverse ways. We can only cover so much in the class, but I'll try to touch on some of the more interesting interactions. All right, so this is, I keep doing that. This is uh, a visual representation of Earth's four spheres. We have the atmosphere up in the sky with the clouds there, the lithosphere, the rocks, mountains, any of the land, I suppose. That's the lithosphere. The hydrosphere being this river or lake. I think it's a river. But also maybe we could look at the snow up in the mountains. That's part of the hydrosphere. And then finally, we have the biosphere with the trees in the background, and then evidence of people, anyway, with these canoes. I think there's one person sitting right here on the dock. But yeah, that's just a visual representation of Earth's four spheres. And then I'd like to play this video. It's a few minutes long. It is produced by the AGI Education, that's American Geoscience Institute. They have a series of videos about Earth science, and this one is about Earth's systems. So I'm going to play this for us. Or I'm going to try to.
You could spend hours scrolling outfits for a last-minute wedding and hope the one you buy feels uniquely you.
This is Big Idea 3. Earth is a complex system of interacting rock, water, air, and life. The four major systems of Earth are the geosphere,
lithosphere,
hydrosphere, atmosphere, and biosphere. Earth's geosphere is made up of its metallic core, solid rock, and also molten rock, soil, and sediments. The atmosphere is the mixture of gases surrounding Earth. The hydrosphere includes water in all its forms: ice, water vapor, and liquid water in the atmosphere, in oceans, lakes, rivers and streams, water in soils, and groundwater. The biosphere comprises Earth's living things, which can be found in many parts of the geosphere, the hydrosphere, and the atmosphere. Humans are part of the biosphere. Human activities can have important impacts on all four spheres. All Earth processes are the result of energy flowing and mass cycling within and between Earth's systems. Earth's energy comes from the Sun and from Earth's interior. It is the flow of energy and the cycling of matter that produces chemical and physical changes in Earth's materials and changes in living things. Carbon, in large amounts, constantly cycles within Earth's systems of rock, water, air, living things, and what we call the fossil fuels of coal, oil, and natural gas. Earth exchanges mass and energy with the rest of the solar system. Earth gains energy and loses energy through incoming radiation from the Sun, heat loss into space, and from gravitational forces from the Sun, Moon, and planets. Earth gains mass from the impacts of meteorites and comets, while it loses mass through the escape of gases into space. Earth's systems interact over a wide range of temporal and spatial scales. These scales can be microscopically small to global in size, and they can last from billionths of a second to billions of years. It's the interactions between Earth systems that have shaped Earth history. They will also determine Earth's future. Regions where organisms actively interact with each other and their environment are called ecosystems. It is ecosystems that supply food, fuel, oxygen, and nutrients needed to sustain life. Ecosystems also provide services such as climate regulation, the cycling and purification of water, and the development and maintenance of soil, all needed to maintain the biosphere. Ecosystems are considered to be the essential support units for life itself. Earth's systems are dynamic. They continually react to changing influences. Parts of Earth's systems seem stable. Some change over very long periods of time, while other parts can change very quickly and have a major impact on living things in the biosphere. Changes in part of one system can cause new changes to that system or to other systems, often in surprising and complex ways. Geoscientists describe some of these changes as feedbacks. This means that they can increase or decrease the original changes and be unpredictable and/or irreversible. Geoscientists' knowledge and understanding of how feedbacks work within Earth systems is still developing. Earth's climate is an example of how complex interactions among systems can result in relatively sudden and significant changes. By looking at the geologic record, geoscientists can see that interactions among tectonic events, solar inputs, ocean circulation, volcanic activity, vegetation, precipitation, and human activities can all cause big and sometimes rapid changes to global and regional temperature patterns and precipitation. And that's Big Idea 3. Earth is a complex system of interacting rock, water, air, and life.
All right, so hopefully we were paying attention there, because I have this quiz question keeps advancing on me. It's probably a setting I accidentally entered. Anyway, I'm gonna let you look at this anyway. Even though it showed us the answer. Which is a natural occurrence not mentioned or depicted in the video we just watched. Earthquakes, floods, glaciers, volcanic eruptions, or all of these were shown in the video. If you didn't happen to see the answer already, I'll just pause for a second here. Feel free to pause the video if you want to think about it. I'll give us a minute. Well, less than a minute. Just so that you can pause if you would like to. Okay, so the answer, all of these were shown in the video, which again, we probably saw already. I don't know if this is going to advance on me. If Earth, in terms of energy flow, is considered open system, closed system, or none of the above. So again, if you'd like to pause to think about this, go back in the video, go back in your notes. If you're taking notes, I recommend taking notes always. But I'm just giving folks a minute to think or pause. All right, so the answer here, Earth in terms of energy flow is considered an open system, right? Remember, we have inputs of energy, that's solar radiation, and then we have outputs of energy, which is radiation being reflected back off of Earth. Okay, so we're going to stop here for this video. And the next one will start by talking about Earth's grid system and specifically talking about some maps themselves. But for this video, this is where we end.